Okay, so in this lecture, I'm going to talk about simulation studies in if you watch the video on distributions in we were able to simulate or generate random variables from a probability distribution, right? So for example, if I want to get a set of random variables from the exponential distribution, I need to specify the sample size, I need to specify the rate or the mean, and then I'll be able to generate those random variables. Okay, remember in R, to generate random variables, we use R, so whatever it is, if it is exponential, RS, and so forth. Now, for an exponential distribution, as I said, you just need RFs like this. So this is what will generate random variables for you. So maybe this is my sample. Then I paste this. So maybe I generate n is equal to 100 and the rate maybe 0.5, 0.5. So it means my mean is what? Yeah, so my mean is 2. So I can now, let's say, look at how my sample is by doing a histogram, sort of, and see. So this more or less looks like an exponential distribution, as must be said. Remember that I said through the inverse probability transform, we can simulate any distribution from the uniform distribution. So for example, the exponential distribution, I can also generate random variables from the exponential distribution by inverting the distribution function, right, of the exponential distribution. If I do so I can also do my, let's say, RS, let me see, my RFs, okay, as this. So I'll write a function. This function should take in just the sample size is enough, right? And then the rate or lambda or the mean. Okay. Now, so this function, I don't even need the, because I can just do it straight away, will be negative. Remember, if we invert it's 1 over the rate, so, but it's negative. So negative log, right? Okay. Then I have, no, I need negative rate raised to the power -1. So that is the inverse of it times. Okay, so let me bring this down. Times 1 minus R unit N. So what I'm doing is that I simulate observations, N observations from the uniform distribution. I multiply it by 1, find the logs, multiply it by negative of the inverse of the rate, and that gives me the exponential distribution, right? Okay. So the same what I generated over there, I could have also generated it using my own function, right? And here I do 100, so n is equal to 100. and then the rate is equal to 0.5. Okay. So I can also say my sample is assigned this, right? And then I can do histogram of my sample, and you realize that this will also follow the exponential distribution. There it is. Okay. Yeah, so I can redo this, do it. Yeah, so anytime, if I even do 1,000, then I'll rather get it will now approach exponential distribution proper as n increases, and so forth. So that's how we can simulate observations from distributions. Either we are writing our own function and so forth. But this is very important in helping us to simulate from distributions using the idea that we can simulate observations from the uniform distribution and be able to use it to generate observations. But what I really want to do is that when we talk of simulation, then it is just that we are now trying to mimic whatever a real life situation on the computer. In statistics, the one of the uses of this simulation is to help us to be able to ascertain whether an estimator is good, okay, and help us select estimators from a host of estimators. So if you do statistical inference, one of the criteria of estimators, we can talk about consistency, we can talk about the standard errors, mean square errors, and so forth. So if you have a mean square error and you increase the sample size, we expect the mean square error to approach zero, then we say consistent. The estimator is consistent, and so forth. Now, it turns out that in generating like or if you propose an estimator in statistics, or we want to compare various estimators, we need to be able to compute some of these things to do that. Okay, it is not every time that you can prove, okay, because I mean, if we find an estimator or propose an estimator, we should be able to generate a standard error theoretically, but sometimes you can't. I mean, it's maybe mathematically intractable and so forth. Now, if I ask you to find the standard error of the sample mean, okay, you will be able to tell me that, well, the standard error is sigma over root n. Okay. However, if I ask you what is that of the median, that will be difficult for you to tell me now. Okay. Now, so in statistics, we have what we call resampling methods, okay, to help us do such estimation. So one of these resample methods is what we call bootstrap. Okay, so bootstrap is just resampling. We resample from the same method. You can talk about jackknife, which is also resampling, but the idea is this, that when we have, let's say, I want to find the standard error of the median. I don't know it. So what I'll do is that if I have a data set, a sample, I will leave one out each time I do the resample. Okay, so if I have 10 samples, I first start by leaving the first sample out. I take the 9 others, I find the median, then so I get 1 median. Then I move on, I leave the second observation out, I find the median, I get the second median. Then I leave the third observation out, I find the median, and so I'll do this until I get to the last observation, which is 10. So in so doing, I get 9 observations, then I'll be able to find the so I have a series of median. I find the standard deviation of those median. That gives me an approximation of my standard error. That's the um, jackknife principle. There's also some leave k out principle where instead of one, we may leave two out and move on. Okay, so for example, what they use in cross validation. So you use, if you have a data set, you split them into training and test, and sometimes validation data sets. So I'm going to demonstrate how we can use, for example, the bootstrap to be able to um, to be able to. Okay, so the jackknife is just leave one out resampling method. Okay, that's what we mean, and then you can have k of them and so forth. So I'm going to look at how we can estimate standard errors and so forth. Then we can make a decision. So here I'm going to compare, for example, moment estimators, moment and maximum likelihood estimators. Likelihood estimates. Okay. Now, so first of all, when I, for example, want to find sometimes the moment and the maximum likelihood will yield the same kind of estimators, right? Sometimes they don't. Okay, so for example, if we say we want um, the moment estimator the for the variance in a normal distribution, okay, that will be our sample estimator for the sample standard variance, so to speak. Okay, now for the maximum likelihood, that will just be just the sum of squares. Okay, sum of squares, sum of squares. Then we divide by n. So you remember that one is n, the other is or n minus one, right? So I can say that I have my moment. Okay. Um, how should I? Let me just use let's see, fit. Let me use an inbuilt function to do this. Uh, okay, so I think we have to use density start. Okay, let's use fit this R. I think I need to install it. Fit this. Yes, fit this R plus package. Okay. Oh, let me see. It's easier. Okay, okay. So I'm going to do this. Quite easy, just using the fit this R. So the moment estimator, you see, it's quite easy. I can write my function. It takes the data, uh, or let's say X. What I need to do is that it will just compute. N is the length of X, and then moment var. So moment variable. So my variance will then be n inverse, right? That's 1 over, oh, sorry, 1 over n minus 1. Just, or let me say, I'm even wasting my time. For x. Okay, so the moment one is just a variance of x, right? Moment estimator. For this is normal distribution, right? So let me just make a comment comparing moment and maximum likelihood estimators for the variance in a normal distribution. Normal distribution. And what I'm saying simply is that, let me see if I can write whiteboard so that it will be clear. Whiteboard, yeah. Okay. So okay. Now, if yeah, so the moment estimator, this is what I'm trying to do. The moment estimator S squared is 1 over n minus 1 sigma xi minus x bar all squared, right? Maximum likelihood, maximum likelihood is which you do as 1 over n sigma xi minus x bar all squared. Okay. Now, the difference here is that you see, if you are doing statistical inference, you can actually find the MSE, okay, of S squared and also and MS of sigma cap squared, right? You can find those, and then you can check the relative efficiency, okay, and then decide that, okay, this one is better than the other. Okay, now that's the concept we are trying to do in R. Okay, here I mean, you are not going to. Okay, so the idea is that it is not always the case that you'll be able to find the MSE of the particular. So if you're unable to do it, what do you do now? You must resort to numerical methods or simulation to do so. So that's the concept I'm teaching now. Okay, so that now we are using this. I'm going to simulate observations. Okay, for the moment one is easy. I'll just find the variance that we know. But for the maximum likelihood, I'm not going to use this formula to do it. What I'm going to do, remember that the maximum likelihood, okay, is that we formulate our likelihood, okay, formulate your likelihood function giving some parameters and mean, okay, then we maximize it, right? So log something, and then, so what we are going to do, we maximize to the parameters, in this case, sigma, the sigma wanted to be sigma squared, right? We set it to 0 and we do that. That aspect, when you set the delta L, okay, over delta sigma to 0, okay, we reduce this problem to a numerical problem. In other words, you may not exactly be able to find the value of that will give you exactly 0, right? So you resort to numerical methods to be able to help you to get to something close to zero. Is that okay? And what that means is that we take the available data, right, and and do that iteration, okay, to get the value of sigma. That will give us something close to zero, and that's it. So that in the numerical approach, it is not a matter of what you do in statistical inference where you just plug it into a formula and you find the observation. But you maximize this based on the available data that you have. Okay. And remember that later on you realize that there are so many methods to do those maximization. Okay. There are so many methods that you can use in doing such um, maximization or minimization in R. Okay, so for example, the fit list R that I did will give you um, some of those routines. Okay, so this is it. If you do um, fit list R, yeah, yeah, this one. Let me see. Oh, okay. So this method. Okay, so this will give you maybe MLE, MME, QME. So you can use any of these. What I really want to okay, so let me move on to what, let's say, Optim, which is the optimization routine. What this optimization, what is this? What is, what is happening? A total social inherit. Okay, so yeah, this is what I'm talking about. So in your mathematics classes, let's say if you do numerical methods, you realize that to find the zeros of a function, there are several methods that you can use. So in R, if you use Optim, the default one is the nil-mean algorithm. But you can have BFGS, CG, LBFGSB, simulated annealing, a whole lot of them, okay, and Brent and so forth. Each of them will have its advantages and disadvantages. So if you go down here, you're going to see, for example, method SUN is developed by so and so. So this is Bellisley 1992. If you come to LFBGS, so the reference is also there. Okay, and so for CG, conjugate gradient methods by Fletcher, and so there are so many methods to I must share this one. There are so many methods to yeah. So this is what I'm saying, that there are so many methods for you to be able to do your maximum likelihood, and those methods are just what will help you to find the zeros of the function. So method nail the mid is usually the default. Sometimes it doesn't work. If it doesn't work, you need to choose another one. But wherever one you are choosing, you must know the conditions, under which such can be used. So for example, some of them require the minimum and the maximum values, okay, where you have to iterate. That's one disadvantage of the maximum likelihood methods. Even though we don't know the parameter, in some methods, you must have an idea of the range, okay, of the parameter. It doesn't mean you give the entire range, then it means your iteration will take a long time to, for example, I know that the variance, when we write the variance of in a normal distribution is greater than 0. So if I give a range of 0 to infinity, I have not really said anything. Okay, so when I have a data set, I must have an idea what the variance will be. Now, how do you do so? You can just use the moment estimators to help you. So if I have the data, I just find a moment estimator for the variance, which is just the normal variance we have. So that will give me an idea of where the variance is. But remember that I said the maximum likelihood does not, take just like a formula just to compute the value, just like we do in statistical inference. On they say find the maximum likelihood estimator, you maximize your function, you get a formula, and then you put it in. What how that is, you use the numerical methods, okay? And this is so for other computational packages like Python or MATLAB or SAS. It's the same principle that is used. The available data, you maximize your likelihood function on it. And that means finding the zeros of that function. That's why it is reduced to a numerical problem, or what we say an optimization problem. Okay, so what I'm going to do is that since fit this R uses the maximum likelihood, I'll just use the maximum likelihood estimator and select the value of what of sigma, right? Yeah, so I can use, let me just use fit this R, yeah, from math package so that we don't use anything. So here, my X is going to be X, sorry, it should be X, okay, X, and then my dense fund is going to be what? Normal distribution, okay. Now, so what I'm going to do is that here, if let me just simulate some observation, X. So X is, let's say, I generate normal distributions, N is equal to, let's say, 30, right? My mean is equal to 4, and then my SD is equal to, let's say, 2, which means my variance is 4. So let me choose something that will be different. So let me say my mean is 10 and so forth. So I generate this. Let me just clear my environment. Okay, I need to do this again. So X, what is manage? So, okay, let's just move on. So my X is there. Yeah, so I find my moment estimator, okay, which is 2.84. Okay, so you see the variance, and my SD is 2, but now my variance will be what? It's what? 2.82, which is different from the 4 that is supposed to be. Remember, what I'm interested in is the variance, not the mean, sorry, not the standard deviation. Okay, now I can use this out to also find the standard deviation. So the standard deviation is now 1.65, right? So yeah, so you see they are different now, right? The moment estimator is giving me 2.8, of course, squared. So let me just assume that I want, let's say, the standard deviation to make like things easier for us. So instead of variance, I'm going to say standard deviation, right? So that we don't need to find the distribution. Okay, so now It means here I'm just going to find SDE, right? So now my moment estimator. Okay, so let me just restart my R. Yeah, R Studio. Okay, just a moment, and I'll restart it to get rid of this. Okay, so our values are already there. Okay, so what I'm saying is that we generate observations. SD is 2, but my moment SD is 2.085, which, sorry, is, yeah, is 2.085. Okay, now I can find the SD for this. So if I want to do that, remember, okay, so let me do this so you know what. Yeah, I need mass to be uploaded in my package. So you see why fit this is not working. It's in mass package. I need to get a mass package running. So there. So that's the SE is 2.05. So you see the moment estimator and the maximum likelihood estimators, they are not the same. Okay. So here I can get my how should I get this? Let me say 2. The second one. Okay. So 2 is SZ mean SZ. Let me see. Just a moment. XD. Okay. So okay. Now let's see. Okay, so what I'm going to do is that I put this as MLE SD. That's what I'm going to do. Then I get my MLE SD like this, and then now I can find the SD of that to okay. So it's giving me the standard error, but I need the 2. Just it's still okay. So just a moment. Okay. Um. Okay. So let's see MSD of 2. Uh, so estimate. Yeah. So I need the estimate, and then after the estimate, I need 2, which is my standard deviation. Okay. So what I'm going to do is that I get the normal estimate through this. Okay. But if you look at this one, you have the maximum likely to give you the let me show you how this is. So if I put the dollar sign to this, the estimate are the parameter estimate. So you have your parameter estimate. Okay. Then you have the SZ of the parameter estimate. And then this is the variance covariance matrix. Log likelihood, for example, those who, if you want to get the AIC and so forth, or use your log likelihood as to measure, of course, that should be the same maximum likelihood estimators because you use the log likelihood to find your AIC, which you can use to ascertain which model is best and so forth. So when you need all of those things, that will be provided for you. Okay. And then the SD as well, which in this case is standard error. However, you should know that it is, as I said, it's not every distribution that you have in R. In other words, this one we have normal. So R can just find the standard errors of the estimators for you quite easily. But in some cases, you may not be able to find it because you don't have it's not a standard distribution in R. So here I am interested if I get the estimate at mean and standard deviation. I'm only interested in the standard deviation. So what I'm going to do is to put this one at the other side of this so that whenever I run my um, maximum likelihood uh, um, uh, uh, routine, I'm only going to get just the standard deviation like that. Okay. All right. So that's it for this side. So now it's like I have my maximum likelihood, my moment SE. So anytime I go back here and I simulate the observations, okay, I can, if I reduce it, I'll realize that my SEs will move away from what? So this one should be mom SE. So let me mom. So maybe maximum MLE.SZ. Then this one is no more variance, but it's SZ like that. Okay. So I run this, I get that one. So if you look at moment MLE.SZ, it will be 1, 2.16, but the moment SZ is on 2.27. So anytime we run this, we are going to get more different values, different values for them. So let me start again. So you see this one is what? 1.53, this is 1.56. I rerun it. Okay. So what it means 1.78, 1.87. Remember the SD here is 2. So from this, if I do it several times, I'm going to get, I can compute the bias, I can compute the variance. If I put them together, variance plus bias squared, I get what? Mean square error, and so forth. Okay, so that's the idea here, how to use simulation to now find what? A particular estimate and also assess it. Okay, so what I'm going to do is that I'm going to, if once these concepts are okay, that we can find this, this, let me do this mom as the named this one. Okay, so I can say numeric so that it takes the name out of it. Oh, sorry, it should be as.numeric. Okay, so let me see. Moment MLES. It's this one that I want to either as.numeric or as.vector, and the name will get out of it because I don't want to get any name. I just want it to be just, yeah, so just a number like this. So I use this as the numeric to do that. Okay, so now MSD is on 2.00, moment 2.11. So if you look at this, then the MLESD is better, right? As opposed to the moment. Okay, but we can't be doing it over. So what I'm going to do is to automate it. Now 2.4, 2.1. If I increase it, and in all this, you must also remember your statistical methods. As M increases, you see they are almost the same, but we expect the maximum likelihood to have a better estimate when we increase the sample size, right? And so forth. So that must also be at the back of your mind. So now what I'm going to do is that I'm going to now automate this in a function form, such that if I provide the sample size, the mean, and the standard deviation, I'll be able to now find this and repeat it over and over and over again. So that's it. So now I'm going to write a function, okay? So that function is going to now um, um, sample size, mean of the normal distribution, standard deviation of the normal distribution. Okay, I can make the mean fixed because we are not interested in the mean. What we are interested in is the standard deviation, right? So we generate it. Of course, we can generate the the distribution from another distribution as well, but that becomes tricky because then we don't know the theoretical um, um, variance. Some of them you can find the theoretical variance. So, for example, if I'm simulating from an exponential distribution, I know the variance of the x once I know the rate, okay, which will be 1 over what, the rate squared. If I simulate from, let's say, a beta distribution, I know the variance. If I simulate from a chi-square distribution, I know the variance and so forth because we know the theoretical variance. So that's the concept we are trying, we can use over here as well. Okay, so I'll say my norm, okay, is a function. To do this function, we'll take sample size, it will take a mean, and then it will take an SD, right? I don't need to use this because these are all functions within. So I change it a bit, and then I have this. Okay. So what I'm going to do is just to put this one inside the function, okay, like this. I put it inside the function, then I have this. Okay. Now, so what do I do now? If I want to do this, right, it means I'm only going to get um, only one sample. But if you are doing this, we should be repeating the samples, okay? So what I can do, if you have checked the videos for S-apply, the apply family of functions, this shouldn't be a problem. So what I'm going to do is that I'm going to put R, which is the number of repetitions. Okay, so I'll start from 1 to R, 1 to R. Then I have the function. Let's say it takes X. I'm not going to do anything to it. I just want to generate functions in terms of R. So this is going to give me, it's going to generate observations, right? That will form a matrix or a matrix with R columns and then N rows. So I'm going to do this just before I do it as a function. I can bring it. What do I do now? To make it easy for you to understand, I'm going to, yeah, give some values to these ones, okay? And then I start so that you can follow each of them. Outside, I cannot do this. I need to put what? Semicolon. N is 10, mean is 10, or let's say N is 20, mean is 10, SG is 2, and then R, let's say we take, usually it must be match, but I have to take something so that it doesn't, let me say 10. You shouldn't confuse yourself with the mean. So let me just put 5 like this, okay? So now let's see. I do this, okay? Now, S apply, it is going to take 1, and then X is assumed to be 1. Then I generate normal distribution. So this should generate 10 observations from the normal distribution. Then I take the next one, which is 2. So it will go on, and because R is 10, it will generate 10 observations, okay, with sample size of 20. So let's look at it. So look at your X now. You see it's numeric. Have you seen it? It has so the rows are the samples, and then the columns are the um, sorry, the columns are the samples, and the rows are the the number, the first number, the second number, the third number. So if you look at it, the first sample is different from what? The second sample, because this is random generation from the normal distribution. So so if we scroll it here, we'll get 10. So those are the 10 samples. So that's the concept or the what the S apply does for us. So what is going to happen is that instead of me to now find the mean, the standard deviation for each sample, I'm going to now what? Do it column wise. So every column, I'm going to find the standard deviation and so forth. So here too, I'm going to use the apply statement. So now I'm going to do apply. Okay. Then I take this X, which is my, sorry, I should just put Y here in order not to confuse people. Okay. And even here, I'll say data matrix. Okay. So that data math, so you are not confused. Okay, so I take my apply math, then the second column, remember, apply has two. Okay, two is for columns, one is for row. But here my samples are the columns, so I must do it that way. So here, my function is just the function that I need, is just the SD. So whatever I did up there, I'm now putting it in a functional form, right? So that I get the values. And this X is dummy, so you don't need to worry about it at all. I could also use Y and say, what this means is that take each column of the math matrix and then find what the standard deviation. Okay, so now I can rerun this. Okay, and then I can run this as well because I'm done with it. Now you will see that I'll get what? How many? 20 because we, sorry, 10 because we have 10 samples. Okay, so if you look at the 1, 2, 3 up to 5, then 6, 7, 8, 9, 10. So these are the values for the standard deviation. Remember, the population standard deviation is 2. You see the moment estimator standard deviation, they are different from the 2. So at the end of the day, we're going to check which one is closer. Okay, so if I want to find the bias will be what? The average of these values minus the mean, which is 2, because that's our population mean, and so forth. If we want to find the variance, we take each of these, then we subtract what? The average value from it as well. Okay. Now, MLE. So now I need to fit my MLE. Each of them, each observation, I'll fit the MLE to it. Okay, find fit the distribution. It's the same apply concept. Okay, so in this course, you don't have to take anything for granted. If I send you a video, you must watch and make sure that you do understand this. So it's the same concept that I'm using, nothing more, nothing less. Okay. So I can put that function in here. So see, it's the same concept. Apply. Each column, take it. Pass that data, the first column through here. Pass it at face.r. Estimate the standard error and then assign it that name. So now I do this one too. I also have the value. Okay. I also have the value now. All right. So I can also check MLESD. There it is. Okay. Okay. So 2.3, 2.1, 1.94. If you check it together with this one, they are not the same. You see, the first sample, this one was giving us 2.36. This is giving us 2.30, 2.34, 2.24, 2.18. So they are different. So, yeah, so that's it. So the estimators give you different results. Remember, the only difference is just the n minus 1 and the n. But you see, because the sample size is also small, you are noticing what? A significant difference between their standard deviations. Okay. So now, what I can do is that I can also now combine these values, okay, in a data frame. So now we come back to some of our concept data frames. Okay, so now I can say my MLE will be these values, okay? And then my method of moments, so mom is what? Mom SZ. Okay. And then I can return this. Okay. I can return it. If I like, I can do everything inside this, and then it will give me just the standard the bias and so forth. But I'm going to run this so that we understand before, and then we will compute the bias outside, mean square error, variance, and so forth. Then when we are done, we can put everything in a function to be able to run without any interaction with it. Okay, so here we compute, let me give some comments over here. So here, generate R samples of size n from normal distribution with um, um, parameters mean and what SD, right? Okay, but here, if in our sense we would have said SD squared, because usually we specify a normal distribution by its what mean and what its standard, sorry, in its variance. Okay, so here what are we doing? Compute the standard deviations, compute SD using MLE and method of what moments. Okay, so we compute it easily, and then here, what is it? Combine values in a data frame. So basically, that's what we have done over here. All right. So now let's see. I am now in a position now to be able to apply my function to generate some, to compute some data set. Okay. Or if I pass a data set to it, I have run it. M norm shows over here. Look at so the functions M norm. There's no red, so I don't have any problem. So how do I deploy this function? If I want to deploy it, I need to call the name, okay, and give it values, okay, and then I get my value. So n, let's take that, let's say n is 10, right? The mean is 2. Mean, let's say 20, and then SD, oh, SD is, let's say 2, and then R. How many repetitions do you want? Let's say 50. Now I should ask you, what do you expect? How many data points do you expect? You know, you should be able to answer that, because remember our our table is to what? Combine the values we find over here. And the value are the columns. What are the columns? The number of what? Samples that we generated. So let's see what this gives us. There it is. So in this case, 50 repetitions. So you see, we have a sample of size of 50. The first one has the maximum likelihood estimators. The second one is what? The moment estimators. So now, if I name this as SD data, okay, I can rerun this. I have 50 of them. This is what? A data frame. So what can I do? I can use apply. I can write a function to compute bias. Remember your bias. Your bias is what? The expectation minus what? The actual value. So what do I do now? If I want to write a function, a bias function, so that from my statistical methods, bias, I'll say bias.fun. Okay, so I take the value, okay, my data, and then I need a parameter, right? So I make it par. Okay, so what I will do is that this will be mean of what? X minus what? The par. That should give me my bias. Okay, the bias, remember, can be what? It can be positive or negative depending on the mean that you are dealing with. What about MSE? The MSE.fan. Okay, I can also find my MSE the same way, right? You see, I can also find the var and add it to the square of what the bias one, right? MSE, but I'm finding the MSE straight away. Okay, so what will be my MSE? It will be the mean, right? So I'm finding the mean of what? X, okay, then minus what? Par. So I take my par, I square it, and that gives me my MSE like that. Okay. So squared, but of course, you find 1 over r of the squared deviations, and that gives you your MSE. Okay. What do we want here? The bias, if it is close to 0, it means that the estimator is unbiased. Usually, you want an unbiased estimator. Okay. If the mean square error, we want the one that is closer to 0. So that's the criteria we're going to use. Okay. So now I have these functions, and if I can do it this way, okay. Once I have these functions, I can apply it to each of these. I'll do it once, and then I'll use the apply function to do it. So bias, okay. I can call my bias function. Okay. Now, what do I need? I need X. X to be my data. So I call the SD data. Okay. And then I select, let's say, MLE. Okay. Then what is my parameter? Remember, the parameter is what? SD. SD was 2, right? So it's 2. I can do it this way. Then I find this. So that's the bias function. The bias for the maximum likelihood is what? Negative 1.55, which means it gives estimators that are lower than the values, the parameter values. Now, the moment estimator, I can also do it. That also gives me negative 0.455. So which one is better in this case? In terms of bias, the moment one is better because it is closer to 0 than the maximum likely. Okay. Okay, so I'm going to also call the maximum likelihood. When we finish, we can put all these together as what? 1, in a function, and then it computes all this. Give it as a table, and then you can now do your interpretation. Right. So the MSE, okay. I also call MSE fan. There, that, and so forth. So I do this. I'm sorry, I haven't, I think, done the MSE fan. There, I had not run it. I wanted to. Okay, so 0.22. This is 0.228. So in terms of MSE, the maximum likelihood is a bit slightly better, okay, because its value is 0.227 as again 0.228. Okay, so that's it, how we compute some of these things. For these two, okay, I can move ahead and combine them, right? Okay, so that for the first one, I can find the, for example, I can use the apply function on the tab, right? Sorry, is the SD data, SD dot data. So I take the second one, and then now I need my function as bias. Yeah, so bias fun, yeah, function X. Okay. Then I call my bias fun or MSC fun. Then my X will be equal to the X that I'm passing in. My par should be assigned to something like that. And then I do this. Okay. So you see, this one computes the MSE of the MLE and the mom at a go. Okay, so instead of doing what is up there, I can do this by just using the apply statement on each of them, and then there I go. My I get my results for the two estimators like that, like that. So now I can now, if I want to put them together, I can put them together as a data frame. So if you study what is going on, I'm now going to put everything in a function to be able to now get values of X. So what I can do is name this as bias dot vec. Oh, that's an MSE. So MSE dot, let's say MSE dot tab, and then I also do bias dot tab. It's not even a tab. This one is a vec. So when you are naming now, you name it sorry, objects. You name it so that it gives some uh, semblance to your whatever you are dealing with, right? So makes it easy. So this is bias, and then so when I run this, I can put them together as a data frame, right? So I can so bias, maybe bias MSC. Now I can now put them together as a data frame, data.frame, and then I have let's say bias vec, and then MSC vec. Okay, so when I do this, I'm going to get something like this. Okay, bias like this. Okay, so MLE, but what I don't know is yeah, so MLE, bias vec, and so forth. But what I should just do is bias is equal to that, and then MSC is equal to this one. Okay, so in that case, when I do it like that, you have it this way. So you see, I can put everything together. So when I run my simulation, at the end of the day, I get the bias and the MSC. Then I can now conclude which one is better, which estimator. So the estimators are my observations, and then bias MSC are my variables in this case. Okay. So what I'm going to do now is to put everything together into my function so that when I run my function, at the end of the day, I'll get what? Just the bias and the MSC for um, each estimator that I want. Okay. And you see, now this is one of the things I was talking about. You see, when I name these, I put them in quotation marks. Now, I don't need to put these functions within my norm function, because maybe later on I'll ask you to do that for, let's say, a beta distribution or a gamma distribution. You still need those bias and MSE functions. So you cannot go into the minor function to get it. So functions that can be used in another or can be used in computing for other things, you don't put them together with your function. And when you do that too, that's a good way of programming, because you do your programs in bits and then you call them together to execute any particular problem. Okay. So this one, because they are all related to the normal distribution, I can now put them within it and be able to find my bias and so forth. Okay. So I'm going to copy this, put them inside, make sure I organize it well, and then at the end of the day, I'll get what I want. Okay, so which is the bias and the MSC. Okay, so let's see. Here we were obtaining. Okay, maybe I should just copy everything and yeah, just copy the function and modify it rather than so I'm going to modify it here and call it in all, putting all together, together, we have this. Okay. So now I'm going to, where I stopped, I'm going to copy what we have discussed up here and then modify it in such a way that I'll have uh, my MSc. That's a go. Okay. Okay. So now let me go back. Okay. So there. So we got to here, right? Tab, right? So when we get this tab, we must now call it the bias function tab of the MLE. So this one, it's not even, we don't need even the tab here, right? We can just use a MomSE. Um, um, yeah, if we don't want to use, so one way, we can find each of them. Maybe I'll go by that so that I limit the way I use apply. So it makes things easier for you. So what I'm going to do is just to put MomSD and then MomSD. Then it means here, I'm also going to take MLESD and replace it with it. MLESD. So if you learn the concept, this shouldn't be. So here we compute what? The bias, we compute what? The variance. So if I like, I can put these together and call it bias vec, right? So what I'm going to do is just to put them in a vector form. So that's that one, then comma, this one, right? Okay, so I do same and name it as what? MSC vec over here. It makes it easier for you to appreciate. Okay, so I change this to what? MSC. So there are several ways to do the same thing in R. Okay, choose the one that is okay for you and do it. Okay, so if I do so, then here I don't even need these ones, right? I don't need this. So I can take it off. Okay. Then what I need now is a data frame that will give me bias rate and what? MSC. So this will work. And then instead of returning bias, we will return what? Tab, we will return this one. So this should be okay for us. Let me see. Yeah. So let's run it and see what will happen. So we do this. It runs successfully. We do it like this. So when you are writing a function to do some of these things, you must run it within the function before now you can go outside of the function. If anything is wrong, you will spot it before you now run it. If you run all of them at a go, it becomes difficult to do it. So I've seen my MSC vec and then the bias vec, right? I've run all of them. Okay, so if you look at it, this is my bias, this is my MSC. Okay. And then now I can put them together, but remember that now they don't have that name because of the way I did it. So you won't have the exact, okay, so it came. Yeah, okay. So then it's fine. Yeah. So that's the bias. Let's see if it corresponds correctly, corresponds to the various. No. MSC. Okay, so let's see. I think MSC, the first one is, you have to be careful, otherwise you will mess them up. So let's see the way these are. So we should get MSC vec like this. So The first one is the moment. The second one um, is the um, yeah. So and then we bring it here. So it should give us so bias MSC. We should get, but we have not gotten any 0.227 there. Something must be wrong. Okay. So you see here, I'm using capital V, but inside I'm using small v. So let me, this is very important for you to notice this. R is case sensitive. And when you are writing functions like this, and then you don't delete some of the vectors because now I have changed them. Okay. Once I change them, they are not reflecting it. This is MSC vec with small letter, but now I was using capital letter, so it doesn't work. That's why if you look over here, my MSC vec is this, but you see my MSC I'm getting is 0.227, but that's not it. So it's giving the old one, yeah. So if I want to get the new one, I must, change these ones to V, right? And then I'll have something like that. Okay, so please take note when you are writing programs, you have to be very careful. So this is it, so MSC of that. So now I see that everything works. So now I can now put them together as my norm vec, my norm dot, let's say MSC. I change it so that it is different from the previous one that I did. I run it like this, okay? I can delete. It's a good thing that when you finish, you delete everything and then you rerun your function, okay? So you have this. I get some error for some cache key, but I think my norm has been done. So the other function that I need for my main function to work was the bias and the MSE. So I need to go and run them so that they are also in the function space. Other than that, I think maybe I should make that mistake for you to know what I'm talking about. So I'm going to run this, okay? My norm MSC. I'm going to call this, yeah, let me use that one. Okay. So we can use this to check for consistency, right? As we increase the sample size, what happens to our MSC? So first of all, I'm using 10. Okay, let's see what happens. So look at this. Okay, so error in bias fan. Could not find function bias. So the first one, remember, the bias function, they are outside this function. And the function is calling them. So I need to run this function to appear so that my norm function will now have access to these functions. Okay. So now it should work now. And yeah, SD there. So that's our bias and MSC. So in this case, yeah, this is what I was talking about. We want the method of moment and then MSC didn't. So I must go back and rename rename the columns. Sorry, the rows of my final this thing. Okay. So what I need to do is to do row names, okay, of bias made, and that gives me um, yeah. So this will be what the first one is method of moment. Let's see, MSC function, yeah, method of moment. Let's see the bias. Yeah, so the first one is method of moment. Method of moment, mom. And then this one is what? MSC. All right. So there it is. Now, but I need to rerun this function for it to take effect. Okay, so I rerun it. I close it, rerun it, and then now I do it. Okay. So now I don't need to even assign this a name, just rerun it like this, and then I get my values. Okay, so that's my method of moment. So in terms of this one, the MSE is far better in terms of MSE and bias. Okay, I can rerun it again. Okay, now the method of moment is better, right? I rerun it again. Okay, now the number of replications, 50 is not so good. I mean, we are doing bootstrapping sort of, so we need more. So I change it to 250. See the method of moment, the bias, okay, getting us good bias, sometimes MSE. I can reduce the sample size to 5, where we know, you see, the method of moments will do a good job compared to the MSE and so forth. Okay, now I can change it to 500, and I think, you see, so this illustrating consistency, go up there and see your MSEs compared to when the sample size is small. Okay, when the sample size is small, you have 0.55 thereabout. When I increase the sample size, you see the MSE is getting smaller and smaller, and so forth. So I can do it like this, so and so forth. So that's how we can put things together. So even though we are looking at simulations, okay, assessing the estimators, okay, we can have some more estimators and check their consistencies and so forth. Okay, so this can be increased. Usually, more than 800 is recommended, right? So, so that's it for this lecture on it. You can try, okay, using, let's say, the gamma distribution. Remember, you can use method of moments. Okay, so try the same thing, okay, using method of moment for gamma distribution, and then also the maximum likelihood for gamma distribution. In your, let me see, in the sorry, let's see, fit this R. I want to check whether we have gamma in there. Yeah, there's gamma. Okay, so here the gamma, you can check what the gamma distribution will have two values, okay, two parameters, I should say, right? Okay, so I can, for example, if I generate observations or whatever we did, we could also, instead of generating the observation, we may also use what? An inbuilt data set, or a data set with a real data set to be used for such estimation. Just that you need to resample from it, and that's not what I did over here. We can use Bootstrap as well when we have real samples. So instead of generating from distribution, we are going to do resample from the data and be able to use it. Okay, but I want to, yeah, look over here. So the gamma distribution, they've done an example here, right? Okay, so our gamma n is equal to 100, shape is equal to this, rate is equal to 0.1. So your alpha and then the beta, which is the rate from this, if you use fits, you see you get two values, but these are maximum likelihood estimated. So look at this one. The shape is supposed to be 5. Look at the shape that was estimated. It's 4.45, right? The rate should be 0.1. It is giving you 0.08 and so forth. So we can, what you need to do is that write a function to compute the moment. Remember the moment you find what the, the mean. Of course, you can find the moment for um, the parameters, okay, for of your shape, and then the rate parameter from what the mean and variance of the sample. So what it means is that you need to now write a function for the moment estimator, right? Okay, so one is alpha over beta, right? And the other one will be alpha over beta squared, right? So you write a function to compute the mean and then the variance. So remember that in this example, when you are doing it, you are going to find the shape, the mean square error for the shape and the rates, okay? Because they will have different values. So please try it, and then you can post it for us to comment on it. Thank you.